So one of the great things about R is that it's a programming language designed for data analysis and statistics, which brings with it a lot of flexibility that you don't have with typical data analysis software, but also a lot of easy access to statistics and modeling and visualization functions, which maybe are a bit harder to work with in more traditional programming languages. And one area where having these two things together is really powerful is when we are looking at simulations and models derived from simulations. So in this video, I'm going to cover some of the key concepts which you need to be aware of and some of the key functions to be aware of when running simulations in R. And I'm going to do this by working through a bit of a case study on a fairly well-known probability problem. This is called the birthday problem. How many people do you need to have in the same room before it becomes more likely than not that two of those people would share a birthday? If you've not come across this problem before, I suggest maybe taking a bit of time, pause the video, go and look into it. If you have come across this problem before, you've probably done an introductory probability course before, because it tends to be the kind of example which comes up here. Because not only is it something which is relatively easy to solve through probability theory, it also has quite a surprising result, because you only need to have 23 people in the room before it becomes more likely than not that two of them share the same birthday. And this sort of problem is one that can not only be solved through the probability theory, it could also be solved through looking at simulations, simulating thousands and thousands and thousands of possible birthdays, and seeing how many times we get a match between birthdays. If you've ever looked into this problem before, though, there's one assumption which is made when working through it, which we know is not a good assumption, which is that all birthdays in the year are equally likely. And this will depend on different countries, but in the UK, the Office of National Statistics, they did some analysis themselves into how common different birthdays are. And there are 1.5 times more births on September the 26th than there are on December the 26th, which is not a trivial difference. And then bring in leap years and February the 29th, and it's going to be a whole big mess. And this is something which is no longer easy to solve just through the theory alone. There's a very nice quote from a paper in 1980 which said, oh, the fastest computer would need 10 to the power of 20 centuries to calculate the various probabilities here. I'm hoping the video that I'm doing today will be a little bit shorter than that, but we're going to go ahead and see if we can first of all use R to solve the birthday problem through simulations as it stands in its classic format, but then modify it up a little bit and show the power of R's flexibility and seeing what happens when we try to make different assumptions and say that maybe birthdays are not all equally likely. Okay, so the first thing that I'm going to need to do is I'm going to need to do something which is going to be different every time I run a piece of code, because otherwise what would be the point in running simulations if I always got the same result every time? And so in the context of the birthday problem, that's generating some random birthdays. So let's just first of all think about how we can generate a random singular birthday. So I could create a list here of every single day of the year and pick from it. Instead, I'm going to save a bit of time by just coding every single day of the year as 1 to 366. And so from this set of 1 to 366, I am going to use the sample function to sample from within it. So by default, I only need to tell it what I want to sample from here. If I press run, what happens is I get all of my numbers 1 to 366, but it randomly rearranges them. So this isn't what I want at all. What I want to begin with is just one birthday. So I can give it a second argument of 1, which will now just pick a single birthday. So day 243 in the year is a random birthday I have generated. And every time I press run, a different birthday is generated. So let's think, okay, about the birthday party problem, where we already know the solution. We already know the answer is 23. So I'm going to start by working through the code here for a 23-person party. So instead of one birthday, I want to generate 23 birthdays. And here we go, we've got 23 different days of the year generated. And I say different days of the year intentionally here because these are actually all different days of the year. And I can press this however many times and I will always get 23 different birthdays. I'm not going to check, but I can guarantee it's true because of one of the optional arguments here within the sample function. And we saw this when we did this without adding that number argument, because by default it samples without replacing any of the elements. So if I asked it for 400 birthdays, it would give me an error because there's not 400 elements to sample from. So here, kind of the key principle here is we want to have different birthdays being a possibility, and we want to fully quantify that possibility. So I need to add in an argument here saying replace equals true. All of my 23 samples in this case will be sampled independently from my set of 1 to 366. So this time it looks the same as I did before, and it would take us a while to spot if there was a problem here. And this is one of the reasons why it's always quite important to look into some of the default options when you're using a new function for the first time. Because spotting that mistake could have taken you a long time, and you could have got slightly confused when you got to results later on. Not all errors generate error messages. Okay, so we've got our sample of 23 birthdays. Every time we run our code here, we get 23 new samples drawn. The next step we need to make is how can we get R to tell us if there is or isn't any matches within that sample. So from our sample function, we might want to pipe it into the duplicated function, because if we have a duplicated birthday, this will be identified by this function. When I press run here, I'm going to get an error. Again, another important principle to remember, that pipe, that is something that we need to have a particular library loaded for, either the Diplo library or the tidyverse library. Always remember to do your setup at the start so that you don't run into errors like this. I'm sure that's an error lots of you are familiar with when you're watching this, seeing you can't find that function, which you know is a function you've used before. So here we go, in this particular sample, we can see we've got a whole bunch of falses, and then we've got one true. So in this case, we do have a duplicate within our set of birthdays. And again, the duplicated function is one that doesn't always work in the way that people expect. So here, there is only one true. It's only identifying it when it becomes a duplicate. So the first time that birthday appears, it's not being flagged as a duplicate. So instead of piping it straight in, let me just look at 2 rows separately. So every time I run this, a new sample will be drawn. So because I kind of want to look at the birthdays and the set of duplicates separately, I'm going to create an object here called birthdays, which I'm then going to look at, and then I'm going to pipe that same object into duplicated, because otherwise we'll have a different sample drawn, and that would confuse me quite a lot. So here we go, this time, no trues, all falses, we got 23 different birthdays. This time you see, there was a true in there, so we can see that the penultimate one, so number 12, is being flagged as a duplicate here. But the first time it appears, it doesn't get flagged as a duplicate. Depending on whether or not, or what you're doing with it, I should say, at the result, this may be something which tripped you up. I think in this case, it's not going to cause us too many problems though, because all we care about is whether there are any duplicates in that list. Because if there are, then we have a match. If it's not, then we don't have a match in our birthdays. So we want to then take the next step of summarising this set of falses or trues into a single value. And this is where perhaps there's a little sneaky trick which I really like using in R, which you wouldn't necessarily think of, but can save you a lot of code here. Because with our falses and trues, these are special class type within R, where the false is equal to 0 and the true is equal to 1. So from this big set of falses and trues, if we consider this as a numerical vector of 1s and 0s, what we want to identify is, okay, is anything true or is everything false? And so if we take the maximum value of this vector, it will be 1 if there is any true in that set. And it will be 0 if everything is false. And this is exactly what we want to code. So all we actually need to do here is pipe it into the max function, and this will now give us a 0 if there is a match, if there's no match, and a 1 if there is a match. So we see 0, 0, 0, 1 that time, 0 that time, 1 that time, and so on. So now we set up our code where we're able to see for one individual simulation whether there was a match. And the next step is going to be Let's repeat this thousands of times and get R to summarize it for us. So what we're going to need to do next is set up a for loop to repeat this process lots and lots and lots of times. Because it's not really sustainable for me to just keep pressing run and run and run and looking at it. We want R to do the heavy lifting for us. So this for loop is a special sort of function within R called a control flow function. So if you start to write for, you'll see it turns blue because it's got a little bit of a special flavor to it, in the same way that perhaps library is a function you've seen before that turns blue in RStudio, because it controls the environment rather than setting individual variables. And within this for loop, we need to set up how we're going to iterate our results. Generally, our convention is to write something here like for I in 1 to 100. And what this means is we're going to create a temporary variable called I, which is going to loop through this sequence of 1 to 100. So it's going to do it 1 loop, 2 loop, 3 loops, up to 100. So if we wanted 100 repetitions, we'd write this. If we wanted 1,000, we'd write this. If we wanted 10,000, we'd write it like this. We could iterate it in a slightly different way over particular elements through a vector, for example. But this is the way that you'll see it written most commonly. It looks a little bit strange when you see it for the first time, but hopefully how to change it and how to modify it is relatively straightforward when you see this is how you write it for 100 iterations. Outside of the round brackets, though, is where it gets quite different. We need a curly bracket or a brace. So we have the round brackets to define the terms of the iteration, and then within our curly brackets, we write what it is that we want to iterate. So within inside our curly brackets here, there's not really any rules about what we write. We can write whatever we like. We can write whatever code we like to go through, but we have to make sure that we get these in the right place. And we'll see as we extend this example maybe a little bit further, you can get a bit confused as to where the start of the bracket should be and where the end of the bracket should be for working out exactly what we want to iterate and what we don't want to iterate. Right now, I think we want to iterate all this process of sampling the birthdays, sampling 23 birthdays, and then summarizing, was there a match, was there not a match? I think I can get rid of that line there of showing the birthdays if I'm doing this 100 times. But otherwise, I can keep my code exactly as it was now without changing anything. So it's always good to write the code for one iteration before you try and loop it hundreds or thousands of times. Make sure it's working once and you're confident it's working once before you do it a whole bunch of times. Especially if you're going to be leaving your computer running for a while if you want to do 10,000 or 20,000 iterations. It can be quite frustrating if you realize you've made a tiny error in your code and you have to do it all again. So let's press run. And what's happened is not much. You can see we've had 100 iterations of I because I has appeared and it's gone up to 100, but nothing else has really changed. We've got a different set of birthdays. What has happened is when you run any code within a for loop, by default you don't see any output. It's run the code, it's done 100 iterations, but it's kept the results to itself. So we've got two things we could do. If we really want to see the results as they come in live, we could pipe this into print, for example. This wouldn't necessarily be a good use of our time, but we can see here it has indeed run it, and the first one there was no matches for birthdays, the second one there was no matches, the third one there was a match, and so on. But again, this is just temporarily printed in the output window. So this doesn't look particularly good to me. What we want to do is we want to capture these results so that we can then do some analysis on it later. And so what I'm going to do is I'm going to set up an object now outside the loop which will capture the results as they come in. So I'm going to call this matches. And this is going to be a data frame. So this is going to have the number of iterations that I'm going to put in a column called rep. And this is going to take the values of 1 to 100. And it's going to have a column called match. And to begin with, I'm going to call match NA, because so far we don't know whether there's a matching birthday or not. So let me run that code, and you can see we've now got a new object in our data environment, which has our iterations from 1 to 100, and it has a column of matches, which is always NA. So now what we can do is, in our code, we can add in to the matches the result from each iteration. So for this step here, instead of having it disappear off into the ether, I can say here matches.iterate. $match, which is the column match within the data frame matches. And what I want here is I want to say the ith element, so I'm going to use square brackets to say that I'm going to do a position-based subset. So within the square brackets, for the first iteration, value of matches $match is going to be the 1 or 0 from the first iteration through the loop. And then the second element is going to be the second observation from the loop. And the third is going to be the third, and so on. This is going to update as we go through the loop. So for example, if I start out just doing the first 10 and then pressing run, if we now look at our matches data frame, we should see we've got 10 here, 10 values of 0s and 1s, which would be the same as we saw printed, but obviously each time is an independent simulation. But then for rows 11 to 100, it's still an NA. So let's fill it in for all of the gaps here and look at our rows 1 to 100, or iterations 1 to 100, and press run. And again, instead of looking at the data frame, what I probably want to do now is look at some summary statistics. So I am going to here pipe from my matches data frame, and I'm going to summarize the mean number of iterations, the mean number of matches, sorry. And again, this is a little trick that a lot of people aren't necessarily aware of, but when you have a binary variable here like a 0 and 1, if you take the mean of a binary variable, that is the same way as a percentage. It's going to tell us the percentage of times that we have a match by calculating the mean of that variable. Again, it's a sneaky little trick which can save you a lot of time. So this is going to be proportion matched. And I'm going to use Summarise here, and I'm going to give it a name because having this data in a data frame could be pretty useful for us later on, as we will hopefully see. So we can see here, out of our 100 iterations, 56% of them were matched. If I run it again, 53%. If I run it again, 54%, 45%, 45% again, 54% again. And what we're probably seeing is that with 100 iterations, this isn't really enough to show us whether or not we've got a convergence. And so this is where we might want to think about, first of all, increasing our number of iterations, but also maybe thinking of our standard error, our margin of error in that estimate. And so because this is a binary variable, we can get the standard error reasonably easily. And this is going to be the standard deviation, and then we'll divide that by the square root of the number of the observations. It's going to be the standard deviation in match divided by the square root of 100 in this case, because we are currently doing 100 iterations. So let me run this again, and we can see our standard error is 0.05. And so a kind of way of thinking about standard error, if you're not sure, is kind of multiply it by 2, and then if you add that on or take it off from our proportion, this gives you a rough range of values where we think the true value might lie. Or we can multiply it by 2, and that's often what we call our margin of error. Again, this is just a rule of thumb. There's better statistical calculations if you really want to think about it exactly. But what this tells us is our margin of error in that 56% likelihood that we're thinking of a match here is plus or minus 10%. So 100 matches is not really going to tell us to any great degree of precision what this value actually is. So let's maybe think about upping it to 10,000 instead. And what we need to be careful of here is, okay, well, let's increase everything to 10,000 every time it comes up. So I need to make sure my data frame is now 10,000 rows, I'm iterating 10,000 times, and I'm taking the square root of 10,000 here. And this will take a little bit longer to run. Only a little bit longer, you see. I was quite quick at doing 10,000 simulations. Think how long that would take to do by hand. Not quite 10 to the 20th century though. And this time round we see our proportion matched. It's 0.51, but our standard error much smaller. Instead of a margin of error of plus or minus 10%, we're thinking more about a margin of error here of plus or minus 1%. So we're pretty confident now that our real proportion, our real likelihood of a match is just a little bit over a half. And if we try and just bring this back to the actual problem, we started out with saying, okay, if we think that there are 23 people in a room, and we think the probability that 2 or more of them have a birthday which is the same is just a little bit more than a half. And indeed, this appears to be matching that result. But what I'm thinking now is, When I just increased my number of iterations, this went up to 10,000. I had to do a bit of manually replacing my code. I know that I want to test this assumption of equal likelihood of birthdays. That's going to mean I'm going to have to modify my code. I kind of want to see what happens if I have 10 people in a room rather than 23 people in a room. There we go, about 12%. There's lots of little tweaks I could be making to my code right now. And I think this is the point where I might want to think about turning this into a function.